In this section, we look at the continuity test. So what is the continuity test? In other words, how do you determine if a function f of x is continuous at a point x equals c? Well, the continuity test has three criteria. The first is f of c has to be defined or it must exist. Second criteria, the limit as x approaches c of the function f of x must exist. And the most important criteria of all is that they must be equal. The limit as x approaches c of f of x has to equal f of c. So next, we have an example. Example 1 has 5 different scenarios, and we need to determine continuity for each scenario. So remember, continuity is to be able to allow you to move your pencil from one area to another area of the function without lifting up the pencil. So let's look at in figure A. We can see that the function value does exist. That's here. So criteria 1 is satisfied. Next, we need to look at the limit as x approaches 1. So as x approaches 1 from the left, the function is going to this value. And as x approaches 1 from the right, the function is going to this value. So they are not equal. So therefore, in this first one, we get that the limit as x approaches 1 of f of x does not exist. So therefore, our function will not be continuous at 1. Let's look at scenario B. In B, our function value does not exist. So here we have f of 1 does not exist. The limit does, however, for those of you who need practice with the limit, as you can see, as x approaches 1 from the left, the function value is going to this height. And as x approaches 1 from the right, the function value is also going to that height. So the limit exists, but the function does not. So therefore, the function is not continuous. Let's look at the third scenario. Well, in the third scenario, we have f of 1 does not exist, and the limit as x approaches 1 of the function does not exist. So we have two conditions that are not satisfied, so therefore the function is not continuous. Let's look at this next scenario. So in this next scenario, we have that f of 1 does indeed exist. It's actually equal to 1 in this problem. And we have that the limit as x approaches 1 of f of x exists. Let's say it's equal to height 2. So the limit from both sides, the function's going to 2, so it exists. So what's the problem? They are not equal. So here the limit as x approaches 1 of f of x does not equal f of 1, so they are not continuous. And in this last one, f of x exists, it's 2. F of 1 exists, it's 2. The limit exists, it's 2, so the function is continuous. Example 2. We want to examine this function and determine continuity at x equal a, b, c, and d. So at x equals a, what is f of a? Well, f of a is indeed 2. And the limit as x approaches a from the left and from the right is going to this height 2. So therefore, we can say yes, f of x is continuous at x equal a. Let's look at x equals b. At x equals b, the problem, oh, f of b does not exist. There's no value at x equals b. The limit does exist though. The limit, as I approach b from the left and right, I'm going toward 4. So since the function value does not exist, but the limit does exist, this function is not continuous at x equal to b. At x equals to c, we have our function value. Our function value, f of c, is 2. And the limit as x approaches c, well, if I approach c from this height, I'm going toward 1. And if I approach c from this height, from this side, I'm going toward 2. So this limit does not exist. So no, this function is not continuous at x equal to c. At x equal to d, not only does the function not exist, the limit does not exist either. So f of d does not exist. This limit does not exist. So no, our function is not continuous at x equal to a, x equal to d. So our areas of discontinuity are x equal to b, x equal to c, and x equal to d. And the only place that f is continuous is at x equal to a. Next example. Example 3, we now have a function that is piecewise defined. As you can see, we cannot use the value of this rational function at x equals -1 and 1. So let's simplify this. This becomes x minus 1. This is x plus 1. And this is x minus 2. And that is divided by x plus 1 times x minus 1. So if we simplify this function, we can see that x plus 1 divides out, and this function actually looks like x minus 2 divided by x minus 1. So for any value that is not equal to -1 or 1, we can actually use the simplified expression for the function. So now let's look to see whether that this function is continuous at x equal to -1. So what is f of -1? So f of -1 is 3/2. We can see that here. That when x is equal to -1, we get 3/2. So therefore, f of -1 is 3/2. And if we look at the limit as x approaches -1, we do that by examining what's happening to the function near x equal to -1, but not at -1. So therefore, we get that the limit as x equals -1 of f of x is the limit as x approaches -1 of x minus 2 over x minus 1, which is -3 over -2. So that's 3/2. So as we can see, the function value and the limit value are equal. So therefore, we can say f of x is continuous at x equal to -1. Now let's look at what happens at x equals 1. Well, f of 1 is defined. F of 1 is 0. And the limit as x approaches 1 of f of x would be the limit as x approaches 1. We're going to use x minus 2 over x minus 1. So that gives us -1 over 0. And oh, there's a problem. This limit does not exist. So since this limit does not exist, we can say f of x is not continuous at x equal to 1. So in example 4, we need to determine where the function f of x is continuous. So we're going to look at values that make the denominator 0. So for us, we can see that the denominator is 0 when x is equal to 0. So f of 0 does not exist. And in fact, we can say then that f of x is continuous on this set, the set of all x, such that x is not equal to 0. So that's set notation, or we can use interval notation, minus infinity to 0, union 0 to positive infinity. In number 2, we're going to factor this. So we're going to get x minus 3 times x plus 3 and then in the denominator, we're going to get x minus 3 times x plus 4. Now we can see that this function does indeed resemble the function x plus 3 divided by x plus 4. But clearly, even if we can factor out the x minus 3, there's something going on with this function because it's not defined there. So therefore, we can see that x squared plus x minus 12 is equal to 0 when x is equal to 3 and negative 4, because these are our factors of the function. So just being able to divide out the x minus 3 does not mean that the f is going to be continuous there. So now we're going to get that f of x is continuous, and we can use this set of all x such that x is not equal to minus 4 and 3. That's our set notation. And our interval notation would be minus infinity to negative 4, union negative 4 to 3, union 3 to positive infinity. In this next example, we want to determine where this function is continuous. Well, let's look at the individual parts. F of x equal to the sine of x is continuous on the interval minus infinity, infinity. We also know that f of x equal to x is continuous on the interval minus infinity to infinity. So therefore, if we take these two functions and combine them, we get g of x equal to x minus the sine of x is continuous on minus infinity, infinity. And I'm going to create a new function. I'm going to call it the sine of x. So I'm just going to let this function be the sine of x, which will be h. So we'll go back and redefine this to be h. Okay. So now we have the sine of x is continuous, x minus the sine of x is continuous. Actually, let's not redefine that. Let's just leave it. So the sine of x is continuous, x minus the sine of x is continuous. That means the composition of the sine of x minus the sine of x is continuous on minus infinity to infinity. Lastly, we want to look at the intermediate value theorem. If f of x is a continuous function on the closed interval ab, and y naught is any number between f of a and f of b, then there exists a c in the interval ab such that f of c must equal the value of y naught. So let's use the intermediate value theorem to show that this function f of x equal to minus 3x cubed plus 9 has at least one zero in the interval 1, 2. So we need to check all the conditions of the intermediate value theorem. So the first we must determine, is this function f of x continuous? So we have our function f of x is equal to negative 3x squared plus 9. And this is continuous on the interval 1, 2. In fact, it's continuous everywhere because polynomials are continuous everywhere. So we know that our function is continuous. Now we need to define a y naught. So the y naught that we're looking for is we want f of x to be minus 3x squared plus 9. We want to see if this value is actually equal to 0. So we're going to let our y naught be 0 because that's what we're trying to determine. Is there a root? So we need to find f of a, which in our case is f of 1. And that's going to give us minus 3 plus 9, which is 6. And then f of b, which is f of 2, is going to give us negative 3 times 4 plus 9. And that's negative 3. Okay. Typo, f of x is minus 3x squared plus 9. So f of 2 is minus 3 times 4, which is 12. And then negative 12 plus 9 is negative 3. So as we can see, negative 3 is certainly less than our y naught, which we said is 0, is certainly less than our 6. So this is f of a, this is f of b, is less than 0, is less than f of a. So our y naught is indeed between a and b, f of a and f of b. So by the intermediate value theorem, there must exist a c in the interval 1, 2, such that f of that c will equal 0. So therefore the function has a root. If we want to look at this graphically, we have that f of a, or f of 1, was 6. And we have f of 2 is negative 3. And so our function has to travel from one point to the other point continuously. So hence, there's some value c, and f of that c is equal to 0. And that concludes the use of the intermediate value theorem.